Welcome to China Gateway, the show where we unpack how real technologies and supply chains move in China and across the world. Grab a coffee and settle in. So today we're doing a deep dive into something pretty significant. It's about a recent successful trial of advanced domestic DUV lithography equipment in China. And this isn't just, hey, a machine turned on. It feels like it signals a real step change, an acceleration in building out a self-sufficient semiconductor ecosystem there.
Absolutely. This is definitely more than just a technical win. Think of it strategically. Access to advanced chips, advanced packaging, that's been a key vulnerability in the whole global AI race, right? Especially with capacity mostly controlled by places, aligned elsewhere. So getting control over the core lithography tool, the thing that actually draws the tiniest features, that's laying the groundwork to really mitigate that weakness.
Okay, let's back up a tiny bit. DUV. For listeners, you get the basic idea of lithography drawing patterns on chips, but maybe aren't sewing in the acronyms. What is DUV? Simple terms?
Right. DUV stands for deep ultraviolet. Basically, it uses a specific wavelength of light, 193 nanometers. And the really advanced tool we're talking about here is an immersion tool, often called AR-Phi.
Immersion, meaning?
It means there's a layer of liquid, usually ultra-pure water, between the final lens and the silicon wafer itself. That liquid helps bend the light more, effectively boosting the resolution, so you can define much, much smaller features on the chip.
Okay, sharper focus, basically.
Exactly. And this tech, DUV immersion, it's the absolute workhorse for what we call mature plus nodes. Think 28 nanometer, still hugely important, 14 nanometer, and even 7 nanometer if you use some clever techniques.
Right, you hear 7 nanometer mentioned a lot with this. So why is this specific type of machine, the lithography tool, considered the absolute choke point, the 7-inch nerve, as some might say? Why more critical than etching or other steps?
Yeah, it's because the exposure tool, the litho tool, dictates the fundamental limit, the absolute minimum size of the features you can print on the chip. Everything else in the manufacturing process flows from that constraint. Deposition, etch, cleaning. None of it matters if you can't draw the initial pattern small enough.
So the feature size determines the density, the power.
Precisely. If the features are too big, your chip density is too low, it uses too much power, it's too slow. Basically, it's not competitive for modern high-performance stuff. Look at the big AI chip race right now, NVIDIA with Blackwell, Huawei pushing its Ascend chips. Often, the bottleneck isn't the design of the chip itself.
Right.
It's getting reliable access to the foundries, like TSMC, that have the capacity to actually make those advanced GPUs or NPUs at scale using the best tools.
Ah, okay. So controlling the litho tool is step one to breaking that dependency.
It's the essential first step. If you can make the tool, you can start building the capacity.
Makes sense. But we always hear about EUV, extreme ultraviolet, as the absolute cutting edge, the future. So why is getting domestic DUV manufacturing capability suddenly such a big deal? Isn't it kind of settling for yesterday's tech?
Not at all. That's a really common misconception. EUV is incredibly powerful, yes, but also incredibly complex and expensive. DUV is still absolutely critical because it dominates huge, high-growth markets that don't need that absolute bleeding-edge performance of, say, a massive server GPU or a top-end smartphone chip.
What kind of markets?
Think about AI at the edge. Smaller AI chips, NPUs, doing processing locally on devices. They need to be fast, but not necessarily that complex. Also, things like radio frequency chips, RF chips for communications, analog power management circuits, which are everywhere.
Okay.
And maybe the biggest one in terms of sheer volume, microcontrollers, MCUs for the automotive industry. Cars are packed with them.
Right, the demand there is enormous.
Exactly. And these applications, they run perfectly well, often best on these mature plus nodes like 28 millimeter, 14 millimeter, even 7 millimeter DUV. It just doesn't make economic sense to use a super expensive EUV process for a relatively simple car MCU. DUV hits the sweet spot.
That really shifts the perspective. Okay, so let's talk about the breakthrough itself. SMIC, a big Chinese chip maker, is reported to be testing this new advanced DUV immersion tool, developed domestically by Shanghai Microelectronics, or SME. What's the real-world difference between saying a prototype runs versus saying it ships reliably, commercially speaking?
Ah, that's the absolute core of it. It runs means, okay, the prototype worked. It successfully processed a wafer. It printed features at the target size. It shows the capability exists. Proof of concept, basically.
Okay.
It ships means something entirely different. It means that machine can be installed in a high-volume factory, run 24/7, meet incredibly tight specifications consistently, and pump out chips with high yield, wafer after wafer after wafer. It's about industrial reliability and scale.
Right, the difference between a lab demo and a factory workhorse.
Exactly. And the sources we're seeing suggest this trial phase, right now, it's probably pretty intense. It's kind of like the early days when ASML and TSMC were first figuring out immersion lithography together. High pressure, lots of tuning.
Moving from science to industrial tool.
Precisely.
So how long does that tuning phase usually take? And what are the engineers laser focused on fixing or optimizing during that, say, 1 or 2 years?
Yeah, historically, getting from that first working machine to something stable enough for mass production, that takes a good solid 1 to 2 years, sometimes longer. It requires really aggressive iteration. And they are hyper-focused on a few key metrics. Probably the most notoriously difficult one is overlay precision.
Overlay.
Yeah, making sure that the pattern printed in one layer aligns absolutely perfectly with the pattern from the layer below it. We're talking alignment accuracy down to just a few nanometers. If that's off, the transistors don't connect right and the chip fails.
Wow, nanometer precision across a whole wafer.
It's incredibly challenging. Then, beyond precision, you need throughput. How many wafers can the machine process per hour? The industry benchmarks set by ASML are way up there, maybe 200, even 300 wafers per hour, WPH.
Okay.
And you need that high throughput while maintaining stability, high uptime, and crucially, high yield. If the machine breaks down all the time, or if it only produces good chips half the time, that high WTH number doesn't mean much. It kills the economics.
That brings us neatly to the business side. From an investor's point of view, or maybe a founder looking for opportunities, why does this specific tuning process actually highlight where the biggest localization needs are?
Because every single time that new domestic machine stumbles during this tuning phase, every time the overlay drifts or a component fails or the throughput drops, it shines a massive spotlight on a weak link in the local supply chain for the components inside that machine.
Interesting. So the machine itself acts like a diagnostic tool for the whole ecosystem.
Exactly. It's like a real-time, high-stakes audit of the entire domestic parts and materials ecosystem that feeds into that complex machine. If a specific vacuum pump keeps failing, you know the domestic pump supplier needs work. If the alignment system struggles, maybe the local sensor or motion control supplier isn't quite there yet.
Right.
And that instantly creates these high-value commercial opportunities. Domestic suppliers can see exactly where the gaps are. They can step in to localize those critical parts, improve them, and crucially, start building robust service-level agreements, SLAs, for maintenance, spares, support.
So it drives the creation of not just the main tool, but the whole industrial support system around it.
That's the key difference. It moves from having a prototype to building a reliable, serviceable domestic industry.
Okay, so this single tool, this DUV immersion machine, is really the centerpiece of a much bigger strategy, right? Building that whole closed loop, materials, then equipment like this tool, chip design, manufacturing, packaging, and finally the applications.
That's the grand vision, absolutely. A fully integrated, self-sufficient semiconductor value chain. And because, as we said, DUV light itself has physical limits, you can't easily draw a 7-nanometer line in just one go. The domestic ecosystem has to get really clever. They rely heavily on these complementary techniques.
Right, the multi-patterning stuff. It
Yes.
sounds super technical. Can you give us kind of a simple analogy for how DUV can actually achieve 7-nanometer features if the light isn't quite fine enough?
Okay, imagine you need to draw an incredibly thin line, but your finest paintbrush is still just a tiny bit too thick to do it in one perfect stroke.
Okay.
So what you do is you cleverly use other materials, you deposit layers, you etch them away in a sequence of steps. You essentially use masks and etching to define part of the line in one step, then define the other part in a second, perfectly aligned step. That's the basic idea behind techniques like SADP, self-aligned double patterning, or sometimes even SAQP quad patterning. Or you might do multiple cycles of lithography etch, sometimes called LELE.
So you're kind of building the fine feature in stages, using the DUV tool multiple times.
Exactly. You use multiple precisely controlled BUV exposures and etching steps to achieve a final feature size that's much smaller than what a single DUV exposure could manage. And reports suggest they're getting pretty good at this, claiming yields of 80% or even better for 7mm processes using these techniques.
Wow. Okay, so the trade-off for avoiding EUV, at least for now, is significantly more complex manufacturing, more steps, more time, but it's actually working well enough to be commercially viable.
It seems so. It's definitely a complex workaround, a sustained engineering effort to push DUV beyond its normal limits. But the strategic imperative is clearly strong enough to justify it. And it's not the only path they're exploring either. They're also hedging their bets, looking at completely different ways to make patterns, trying to potentially leapfrog optical lithography altogether.
Really? Like what kind of alternative path?
Well, they're putting serious effort into things like nano-imprint lithography, NIL. That's where you basically physically stamp the pattern onto the wafer resist using a template, like a microscopic printing press.
Huh. Stamping instead of shining light.
Right, and also things like multi-beam E-beam lithography, using electron beams instead of light. Now, globally, some major players explored these and maybe shelved them due to challenges with yield or throughput in the past. But in China, these seem to be viewed as potential alternative routes, ways to maybe bypass the extreme complexity and supply chain control associated with EUV light sources.
Interesting. Okay, so if the main DUV tool is getting closer to localization, and they have these workarounds and alternative paths, what are the key remaining gaps? Where are the export controls really biting now? What are the specific high-value bits and pieces?
Right. This is crucial for anyone looking at the supply chain or investment opportunities, because these bottlenecks are precisely what global restrictions are often targeting. It really boils down to a few key areas of high-precision systems and critical materials.
Okay, like what?
First, optics and metrology. We're talking about the incredibly complex lenses and mirrors within the litho tool, but also the standalone measurement and inspection systems you need throughout the fab to check alignment, find defects, measure film thickness, super precise stuff.
Makes sense. What else?
Second, high precision flow control. This sounds mundane, maybe, but it's critical. Think about etching or deposition processes. You need to control the flow of highly reactive gases with incredible precision and consistency. So that means specialized high-precision flow meters and, really importantly, corrosion-resistant high-speed valves that can handle these nasty chemistries reliably for years.
Why are simple things like valves and flow meters so hard to get right? It sounds like advanced plumbing.
If only. It's anything but simple. Imagine trying to control a flow of corrosive plasma gas down to fractions of a percent, second after second, day after day, to ensure every single chip gets exactly the same etch depth.
Okay, consistency is key.
Absolutely. The material science to make components that don't corrode or degrade, and the mechanical precision to control flows that accurately. It's very specialized expertise, and we've already seen this playing out. Critical vacuum system components, like specialized vacuum gauges from suppliers like MKS, apparently got cut off, forcing faster domestic development. And for other crucial bits, like vacuum transfer systems, the robots that move wafers between tools and vacuum suppliers like Brooks have reportedly stretched lead times out to 2 or even 3 years. That basically forces localization.
Right, long lead times become a kind of de facto control.
Exactly. And the final big category is materials, especially the advanced photoresists, the light-sensitive chemicals coated on the wafer, and all the other specialized processing chemistries needed. You can have the best litho tool, but if your resist is inconsistent or performs poorly, the whole process falls apart.
Okay, that paints a clear picture of the remaining challenges, which are also the opportunities. So let's pivot to the actionable side. For the founders, the operators, the investors listening, how should they actually assess this changing landscape? How can they capitalize? What's the checklist?
Okay, first things first, market fit. Understand where the immediate domestic demand is for chips made with these new DUV systems. As we discussed, it's primarily in 4 hot areas right now: AI, edge computing chips, RF and analog circuits, power management ICs, and automotive MCUs. If your product or service feeds into those end markets in China, you've got a clear runway driven by this localization push.
Got it. Focus on where the chips will actually be used first. What's next?
Second, if you're evaluating a new domestic equipment supplier, maybe not just a litho tool, but etch, deposition, whatever you need to insist on seeing a clear proof path. Don't just take their word for it. Yes, you need evidence of successful pilot runs in a real fab, but critically, you need to verify they've achieved stable overlay precision if it's a litho-related tool. That's non-negotiable.
The alignment accuracy we talked about.
Exactly. And then you need proof they can maintain high throughput at the required yield targets. Aiming for that 80% plus yield floor for advanced nodes like 7nm. Capability is one thing, consistent high yield production is another.
Okay, proof path,
Yeah.
pilot, stable precision, throughput at yield.
Yeah.
What about the service and spares angle we touched on? That sounded like a big, maybe underappreciated opportunity.
It is huge and often gets overlooked when everyone's excited about the main machine. Reliability is the next mountain to climb after you've proven basic capability. So operators looking to adopt domestic tools need to focus intensely on service and spares readiness. Look for suppliers who aren't just selling hardware, but are building professional service level agreements, SLAs.
Right. What does that look like practically?
It means focusing on metrics like high mean time between failures MTBF, how long the machine runs before breaking, and critically, short mean time to repair MTTR, how quickly they can get it fixed when it does break. This requires investment in local service hubs, well-trained field engineers, readily available spare parts. It's a whole support infrastructure.
And that infrastructure itself is an investment opportunity.
Absolutely. For investors, some of the most robust entry points right now might actually be in localizing these critical, often lower volume but high value, restricted components and the associated services. Think beyond just SME making the litho tool. Look at opportunities like setting up joint venture service hubs focused on maintaining specific types of domestic or even imported equipment. Directly localizing those high-precision parts, we talked about the specialized vacuum components, the flow meters, the valves, manufacturing advanced photoresist and other critical processing chemistries locally. And don't forget the essential supporting infrastructure. Things like contamination control systems for the clean room and fab automation systems, the software and robotics that run the factory efficiently. These are all crucial pillars supporting that self-sufficient loop.
DUV matters, domestic immersion is real, and the investable next steps are parts, metrology, chemistries, and services, and ecosystem information.
Exactly. And maybe here's a final thought, sort of building on that. We know the ultimate long-term goal is domestic EUV. It's sometimes referred to by the codename Everest. It's the peak they're aiming for. Now, given how quickly this DUV immersion breakthrough seems to have happened, it genuinely caught quite a few industry watchers by surprise. Maybe critical thinkers should start asking, could that EUV project also accelerate? Most predictions put domestic EUV capability out towards 2030 or even later. But if all these underlying ecosystem components, the precision parts, the materials science, the service infrastructure, if they mature faster than expected because they're being aggressively developed and proven out for DUV right now, well, maybe that ultimate Everest goal could end up being closer than many people are currently willing to admit publicly. Something to think about.
Thanks for listening to China Gateway. If you're exploring China-facing tech, supply chains, or partnerships, subscribe and leave a comment about what you'd like us to dig into next.